Hey everybody, point of this video is to get you through some solutions to the quadratic regression quiz on cancer rates in males in the US. So here's your data from the quiz. I don't have the TI hooked up to show you, or a Excel spreadsheet hooked up to show you, but the reason we're looking for quadratic type behavior here, if you look at the years, we're skipping by about 5. It's 5 and then 4. But if you look at the data, it's going up and then back down. Now it's not a huge number up and huge back down, but it's definitely not linear because it's taking this kind of a shape overall. So what I've got you doing is running those data through your TI to get a quadratic regression. So I'm assuming you've already done that. The first question, it asks you to find an average rate of change. An average rate of change in these cancer deaths per 100,000 from 1990 to 1995. Now I know we spent a lot of time in class using the TI to do this. We also did them manually, but it's so, once you start getting into functions like this, you don't want to do them manually. It's too easy to screw up some little tiny arithmetic thing. So the big idea about an average rate of change calculation is this, is you're forcing linear behavior on not necessarily linear data. So 1990 falls in here, 95 falls in here. So you have to, first of all, predict what 90 and 95 are, which the TI can do just fine for you. Any technology can do just for you. And then you have to divide that by the change in years, which is 5. So the easiest way, and this is what we did in class, was we took the value of the function at 1995 and took the difference from the value of the function at 1990. That will tell you the change in numbers of cancer deaths from 1990 to 1995. You can also go in a different order, it doesn't matter, but I just chose to do it that way. It's because 1995 is bigger than 1990. And then you divide by 1995 over 1990. And the reason you do this is because it's the rate of change. This is your rise, this is your run. So it's basically going to linearize the behavior of the number of deaths per 100,000. When you analyze that, you end up getting, I got about negative 1.6. which doesn't tell you a great deal of anything by itself. That's why I said explain what it is. And what it is on average from 1990 to 1995, okay, per year, the number of cancer deaths per 100,000 men dropped about 1.6. So we lost, in each of those years, on average, from 1990 to 1995, we lost about 1.6 men per 100,000 less due to cancer, which means cancer numbers, I should say, were falling from 1990 to 1995. 1.6 guys less per 100,000 per year. That's what that using the per twice was talking about. Fair enough? Cool. All right, next question. How many guys died from cancer in 2011? Looks like I ran through the model. We got about 123.7 men per 100,000. Per 100,000. That's simply just running the number 2011 through. We'll come back to the potential issue with that momentarily. Next one is, according to American Cancer Society, we actually lost about 300,000 guys in 2011. Okay, we'll come back to that because that is clearly different than what our number came up with. Question C, how many U.S. men are there? I gave you some hints about how to Google for this. The easiest thing to do is just go into Google and type number of U.S. men or number of U.S. citizens or number of Americans. Number of Americans divided by 2, number of U.S. men, it'll give it to you. It's around 150 million. Roughly half the United States population is male. So 150 million. Unit analysis, so 150 million. This might have confused some of you. If you have 150 million, that's 1,000, there's a million. I say change that so that it's out of 100,000 to make it match the unit that's up here. So you're going to take your decimal point and move it back. So that's tens, hundreds, thousands, 10,000s, 100,000s. So 150 million is really 1,500 100,000s. It's stupid to say that, and you would never say that. You'd say 150 million, but because this unit is per 100,000, we want to make this unit match it. And then I tell you to multiply that number by the 123.7 men per 100,000. So you can see why I did that. If this unit is men per 100,000, and this is 100,000s, the 100,000s are going to cancel, the unit's going to cancel, and you're left with men. And when you multiply that out, I got about 187,000 guys should have died from cancer in 2011, which is obviously wrong. It's half of what actually happened. I mean, we lost 300,000, and I'm saying it should have been 187,000. And then that's where part E comes in, the percent error, and then explain the difference in the error. So as far as the percent error, all you've got to do is run that number into the regression predicted result. And then the ACS estimated value is the 300,000. So that minus 300,000 divided by 300,000, I end up getting around, I said it was half. It's not quite that. It's more like negative 40%, which means I was under by 40% with my estimate as to what actually happened. That's pretty significant, you know, being off by that far. Well, how could it have been off so much? How could you be off so much by it? Well, fairly straightforward, actually. We took our model, which ended in 1997, and assumed that that behavior continued all the way to 2011. Go Google the actual cancer deaths and see if they follow the parabolic pattern, and you'll see that they don't. So, again, the big takeaway is wonderful mathematics, fun, wonderful mathematics, very, very enjoyable. But the kicker really is that you don't want to assume too much about what the mathematics can and can't do. Okay, you can't assume that behavior is going to continue indefinitely into the future if you can't prove that it does. So be careful. Be careful always. Hope that helped.